examples of integral extensions.
All right. Well, first of all, thank you all for being here. As you said, my name is Nicholas Camacho. I'm a second-year grad student at the University of Iowa. I'm currently working with Dr. Frauke Blair, and in the background reading phase of our research, so I haven't gotten into the big stuff yet. And so what you'll see today is as I said in my abstract, it's just some basic things that I've been learning these past few semesters, some things in ring theory, some things in number theories, there's even some things here in algebraic geometry. Oh, okay. Has to reload. Okay, great. So so instead of going for 20 minutes and then leaving 10 minutes for questions, I'm going to go for about 25 to under 30 minutes, and would encourage questions as I go along. If there's something that you don't understand, I'd be happy to explain it, go back to use up the 25 to 30 minute time that we have together. So please give me your questions as we go. All right. So outline. The first thing we're going to do is define what integral means, what integral elements are over a ring. The second thing is introduce the norm and trace of ring elements, which is going to come from the trace and determinant of a matrix. We'll get to that. And then using these first two, we're going to find cyclotomic integers, which I will define as we go. And then we're going to talk about curves. So very simple. Let's get started. Integral elements over a ring. What are they? So just say all of our rings are commutative, have a 1, have all the nice things that they should have to make everything work. So R is a ring, S is a subring. An element in R is integral over S if there exists a monopolynomial with coefficients in S of which A is a root. So this is the same thing as a similar thing to algebraic. An element is algebraic over a field if it is a root of a polynomial with coefficients in that field. And so the picture that you should have is we have the ring R, S is a subring, and so I'm going to collect, so in other words, there are elements in the ring S such that A is a root of the following. And so a fact, and whenever I say fact, it means I'm not going to prove it. It's a proposition or a theorem in some book that the elements of R that are integral over S form a subring of R containing S. And so the picture you should have is R is here, S is here, and so there's this ring, subring S prime that contains S that contains all the elements that are integral over S. All right, and so as I just said, the elements S prime contained in R that are integral over S is called the integral closure of S in R. And so this is another picture diagram that you should have in mind. You have R, the big ring, it contains S prime, and that contains S. In the case that S is an integral domain, the integral closure of S is, without any reference to the ring, is the integral closure of S in its fraction field. It's a domain, so we can look at its fraction field. And so again, we have the same picture. We have S down here, domain, its fraction field, and in between you have this S prime. These are all the elements of the fraction field that are roots of some polynomial with coefficients down in the bottom. So if S is integrally closed, it just means that this S prime and S are actually equal to one another. It means that all the elements of the fraction field that are integral over S is S itself. So let's jump into some examples. So the integral closure of Z in Q is itself. So that means if I tell you that there is a element of Q that is integral over Z, then you know that that thing I started with was just in Z to begin with. So Z is integrally closed in Q. You don't get anything more by looking at integral elements of Q over Z. And so the interesting thing we want to do is we want to look at field extensions of Q and then say, okay, what are the elements of that field extension of K that are integral over Z? Because we don't get anything more if we just look at the integral closure of Z and Q. And that ring, that subring of K, is the ring of integers in K denoted by this OK. So again, the picture is Z. It's contained in Q, but it's also contained in this field extension of Q. And there's some ring in the middle called the ring of integers of K. All right. And so some explicit examples. The integral closure of Z in Q adjoin square root of negative 1 is the ring. Any guesses? Z bracket I. Yeah, Z adjoin I. Okay, so let's look at another one. What about the integral closure of Z in this quadratic field? What do you think? Yeah, so it's a, what he said, Z adjoin 1 plus root 5 over 2. And at first, when I was first working with these, I was like, oh, it's probably just Z adjoin the square root of 5. But there's a classification that shows, depending on, when it comes to the case of quadratic extensions of Q, it depends on the congruence of what you're taking the square root of mod 4. So 5 is congruent to 1 mod 4, and so this is what the quadratic integer ring in this case looks like. Okay, so we are going to, the first half of the time that we have left is going to be explicitly computing the ring of integers in a cyclotomic field. And so that's where you would join a pth root of unity to Q and look at the ring of integers there. But before we get there, we need to discuss some things about the norm and trace of ring elements. And instead of defining them explicitly, I'm just going to start off with an example and let the example help you understand what the definition is. Because I could give the definition, it's very, but examples are better. Okay, so let R, our bigger ring, is Q join root 2, and S, the smaller ring contained in it, is Q. So R has an S basis 1 and square root 2. So if I take an element of R, so Q join root 2, it has this form, A plus B root 2. So A and B are in Q. And then when I look at what multiplication of U by each of the basis elements is, we have these formulas. And so as I mentioned before, the norm and trace come from the determinant and trace of a matrix. So in the same way you take a linear map over a vector space, there's a matrix corresponding to that linear map. And what do? You see how it acts on the basis elements, and then you get the columns or rows, depending on which you like, of the matrix to represent the linear map. And so the linear map we're considering is multiplication by this U. And so the map multiplication by U from R to itself has this corresponding matrix because of the way that U acts on the basis elements here. And so we say that the trace of Q join root 2 over Q of the element U is the trace of this matrix. And the norm of the element U is the determinant of this matrix here. So that's the norm and trace of an element. You are assuming that one ring has some kind of basis, so it's a free module over the smaller ring, and you can do this construction for any ring over another ring, or module over another module over a ring that has a basis. Okay, so some facts about the norm and trace. Supposing that R as a module over S has rank n, the trace is additive. So it's exactly what you think. Trace, you're used to trace being additive with matrices, so all these facts come from things that you know about matrices. Trace is additive. Also, V being in the ring in the bottom, the smaller ring, it's linear over S. So I can pull out scalars from S. And if I take the trace of an element V, which is in S, I just multiply the rank, and this will come up later, the rank of R over S times V. The norm is multiplicative, because it comes from the determinant. And if I, again, plug in V, which is something in our bottom ring, into the norm, I just raise it to the rank of R over S. And I can pull out scalars from the norm at the cost of raising it to the rank, and that comes from the multilinearity, the n multilinearity of the determinant of the determinant. So here we go. So some setup. Now that we know a little bit about norm and trace, let P be a prime and zeta be a primitive pth root of unity. So since it's primitive, it's not equal to 1, and so it's a root of the following polynomial. And this polynomial is called the cyclotomic polynomial. And so as a fact, we know that, which I won't prove, that this polynomial here is irreducible over Q. So what does that mean? When I look at Q adjoin zeta over Q, it has degree, the minimal polynomial for zeta over Q, which is P minus 1. And as a basis for Q adjoin zeta over Q, I have the following. 1 zeta, zeta squared, all the way up to zeta to the p minus 1 less than the degree of the minimal polynomial. And so, recall, I put it in quotation marks if you haven't seen, but recall that what do these elements in this field really look like? They look like linear combinations of the basis elements with coefficients in Q. And Z bracket zeta is a linear combination of the basis elements of Z bracket zeta over Z with coefficients in Z. So these are almost the same, but not so much. This is a field and this is a ring. And you only take coefficients in Z here. Okay, then this will come up. All right, so our goal is going to be to describe the elements of Q adjoint zeta that are integral over Z. And so, spoiler, look away if you don't want to know, if you want it to be a surprise. We are going to show that the cyclotomic integers, the ring of integers in Q adjoint zeta is, close your eyes, Z bracket zeta. Yeah. All right, so let's get going. So first we need to calculate some traces. So since this is an irreducible polynomial, we can use the following fact. Again, something which I won't prove, just some facts about the trace. If E is a field and I have an element that's algebraic over E, and I have this expression for the minimal polynomial for U over E, then the trace of U with respect to these fields is the negative of the second coefficient in its minimal polynomial. And the norm is, and we won't use this fact, but I thought I'd put it here for completeness, the norm of the element is -1 to the degree of the minimal polynomial times the constant term. And if you would like to know how to prove any of these facts, anything I say today that I'm not going to prove, I'd love to talk to you after. We can discuss whether it's true. So, what is the trace? Anyone want to tell me what's the trace of zeta? Knowing that this is its minimal polynomial, what is the trace of zeta? Yeah, -1. It's the negative of the second coefficient here, so -1. And earlier we said that if V is an S or a bottom ring, and we're taking the trace with respect to R over S, we just have to multiply the rank of R over S times that element. And so if I look at 1, 1's definitely in Q. So the rank of Q adjoint zeta over Q is P minus 1. So I just do P minus 1 times 1, and so the trace of 1 is P minus 1. All right, so what we have is that the trace of zeta is -1, and the trace of 1 is P minus 1. And so since the powers of zeta are conjugate to zeta over Q, and by conjugate I mean Galois conjugate, then they have the same minimal polynomial, and hence they have the same trace from the proposition we saw in the last slide. And so the trace of zeta to the j is -1 for all j between 1 and P minus 1. And because the trace is additive, the trace of 1 minus zeta is the same as the trace of 1 minus zeta to the P minus 1 is P minus 1 minus -1, which is just P. Okay, so I'm throwing a lot of facts at you, and as we need the facts later on in the proof, I'll put them back up to remind you. Okay, some more facts. So we're going to write TR just in place of the trace of Q joins zeta over Q. Let G be the Galois group, and some facts here again that I won't prove, but if you're interested to talk about, I'd be more than happy to talk about with you after. The trace of an element is just the sum of its Galois conjugates. Of all the Galois conjugates, which I think is really cool. If Y is integral over Z, then its trace has to land back in Z. And the last thing, which is not too hard to show, but it's just the ideal generated by 1 minus zeta in the cyclotomic integers intersected down with Z is just PZ. So for those of you who know about ideals lying up over other ideals, this is just saying that the prime ideal 1 minus zeta in the cyclotomic integers lies over the ideal generated by P. And again, as we need these facts, I'll put them back up on the screen. And so corollary, I call this a corollary because we're going to prove it. It's not just a fact that I'm asking you to believe me on. And the corollary is that for anything that is integral over Z in Q adjoint zeta, the trace of that element times 1 minus zeta lies in PZ. So let's prove it. So we're going to just call the sigma j's the Galois group of Q adjoint zeta over Q. And just assume that we've indexed them in such a way that it sends zeta to the jth power of zeta. And just for simple notation, assume that the jth element of the Galois group sends U to some other element, call it Uj. Okay, so let's look at the trace of u times 1 minus zeta. We're going to use this fact. I said that the trace of an element is the sum of its Galois conjugates, so I'm just going to apply sigma j to this element and add them all up. And so this is a ring homomorphism, so we can apply it to u and to 1 minus zeta, and we get this uj based on our notation from here, and 1 minus zeta to the j. All right? And so that 1 minus zeta to the j, a common formula that you may be aware of, is that that's just equal to 1 minus zeta times this sum. So we're going to just change this difference. The only thing I've done is change it to this product. Okay. So I haven't changed anything. I just shortened the line here. So we have the same thing here for the trace. Now we're going to use these two facts, that being integral over z means that your trace is in z. Now we're assuming u is integral over z, 1's integral over z, and negative zeta is integral over z. And they form a ring, so this whole element is integral over z. So what that means is that this sum, whatever it is, this sum is integral over z, and so its trace has to be, that this element is an element of z. Now, what's highlighted in orange, those are all in the cyclotomic integers, and so what that means is that this sum is actually in the ideal generated by 1 minus zeta in the cyclotomic integers, but I also said that it lies in z, so it's also in z, which by our third fact is pz. So we proved what we wanted to prove. Okay? All right. So, main theorem. Let's do it. Let's show it. Let's show that everything in the field q adjoins zeta that is a root of a monic polynomial with coefficients in z is the ring z adjoin zeta. So, we're going to take an element, u, in the cyclotomic integers. And so what that means is that it has this expression, and that these ai's all live in q. And what we're going to do is show that all the ai's actually live in z, and then we'll be done. That's our goal. So let's look at u times 1 minus zeta. Since we just proved something about the trace of such an element, let's look at what it would be. So multiplying this expression by 1 minus zeta, this is what you get here. All right? And so what that means is when I apply the trace to this, remember the trace is additive, so we can break it up across each term. And since we're taking the trace over q adjoins zeta over q, means I can pull out all these ai's. Show it here. And then again, I just moved the trace in from this step to this step. I just moved the trace into here, because again, it's additive. But we're going to use the fact that we proved before that the trace of all the powers of zeta are 1, that they all equal one another, and they're negative 1, and the fact that the trace of 1 minus zeta is p. So what that means is so this is equal to this here, so all these terms except for the first one fall away, and what you're left with is a naught times p, since the trace of 1 minus zeta equals p. Okay? Let's just shorten this. So again, we just showed that the trace of u times 1 minus zeta is a naught times p. And remember our corollary that we proved, we said that the trace of u times 1 minus zeta is in the ideal generated by p in the integers. And so what does that mean about a naught? It lies in z. All right, so we just showed we have a lot of work to do, because we just showed that a naught is in z, but now we got to show that a1 up through a p minus 2 is in z. But here's a cool trick. So since the inverse of zeta to the p minus of zeta is zeta to the p minus 1, and the cyclotomic integers form a ring, then zeta inverse is in the cyclotomic integers also. And excuse me, I misspoke. Not because it's a ring that the inverse lies in there also, but it's because zeta to the p minus 1 is in the cyclotomic integers, and the inverse of zeta, which equals zeta to the p minus 1, is also in there, because zeta to the p minus 1 is in there. Okay. So now consider this. U minus a naught, so u, a naught, and zeta inverse are all integral over z. So when we multiply them, we still get something that's integral over z. We get this expression. We get a1 plus a2 zeta all the way up to a p minus 2 zeta to the p minus 3. So as I just said, these are actually integral over z. But this expression looks an awful lot like this expression here, right? Just 1 degree less. And so by the same argument that we just went through, we get that a1, the constant term of this expression, is in z. And we can keep doing this. And so it's not that much work. We just had to really prove it for one case and then use this trick here to get that a1 is in z, and then a2 will be in z by a similar trick, and we can repeat this process to show that all the ai are in z. So this element that we assumed to be integral over z really had all of its coefficients in z, and so we've proven what we wanted to prove. Is there any questions there? Cool. All right, so let's, in the last 5, 6, 7 minutes, let's talk about curves, because I promised we would talk about curves. All right, integrality and algebraic geometry. So we're going to take a polynomial in 2 variables that's non-constant and irreducible, and I could replace C here by any algebraically closed field, and everything I say will be the same. But let's just stick with C for concreteness. Sure there's no questions about what we just did? No? All right. So we're going to define E to be the fraction field of this quotient. Now since F is irreducible, we know that this quotient really is a domain, so we can actually look at its fraction field. And we're going to look at the following diagram. Now, you shouldn't believe me immediately that C bracket X really does live inside this vertical arrow indicating that it really does live inside here, but with appropriate assumptions on F, it will. For example, that it's not a linear polynomial on X, and yes, and so when F is not a linear polynomial on X, this naturally lives inside here through including the polynomial in one variable into the polynomial ring in 2 variables, and then quotienting out, and you get that composition is an injective map. So in that way, it really does live in this quotient. Remember, E is the fraction field of this domain, and C adjoin X is the fraction field of C bracket X. So we have this diagram, all right? And so, as I said, with appropriate assumptions on F, this diagram really does make sense. This quotient really does contain an isomorphic copy of C bracket X, and moreover, E contains C adjoin X. All right, and so with more appropriate assumptions on F, and this is that it's monic in the variable Y, we get that this ring is actually integral over C bracket X. And again, I'm just telling you these things. If you'd like to know why, I'd be more than happy to talk about that. So now, our goal is going to be to say that, okay, we know that this ring, this quotient, C bracket XY mod F, is integral, contains, and is integral over this ring, but is it the integral closure of C bracket X inside this field? So, in other words, if B is contained in E, is the integral closure of C bracket X in E, then we have this inclusion. Right? So again, the same assumptions here. So the natural question is what? What is the natural question here? We have this containment, so what do we want to know? Yeah, when are they equal? So when do we have equality? When does this tell us all that we want to know about the elements that are integral, the elements of E that are integral over C bracket X? And so, let's look at some pictures, and I'll have you tell me what you think the answer is. So, we have 2 polynomials here in 2 variables, y squared minus x cubed minus x squared, and the other one here. They're both curves. And so set them equal to 0, look at their 0 set. So when f is either one of these polynomials, I'm telling you that this ring is not the integral closure of C bracket X in E. In other words, it does not equal B. Okay. All right, let's look at another. We look at these elliptic curves. If our polynomial f is either one of these polynomials, we do have that this ring is the integral closure. We do have it, is the integral closure of C bracket X in E. So, again, our question was when is this quotient the integral closure of C bracket X in E? When do we have equality with that in B? And so based on these pictures, what do we think the answer is? Yeah, something to do with smoothness, absolutely. So if, and only if there's any doubt. The curve associated to f is not singular. And so I really like this because it says that a very algebraic thing, we defined integrality of one ring over another, just completely in terms of polynomials and just ring theory. This desirable algebraic property of this ring over this ring, C bracket x mod f, C bracket x y mod f over C bracket x, it has this nice algebraic property if the curve associated to f is nice. And so you have a nice algebraic property corresponding to a nice geometric property. All right? So, all the things I talked about today were from these two books. And so, I really do, this is a book that was translated from the French, which is really cool. And this is I'd highly recommend this book. It's very detailed. Lawrencine does a really good job. So, thank you.
So we have a couple of minutes. Is there any questions for the speaker?
Is that last statement that doesn't extend to higher dimensions, right?
I don't believe so. I don't believe so. Yeah. Okay, yeah. No, it does not. Or,
What are you doing with these?
yeah, so as I said at the beginning, I'm in the background reading phases, and with my advisor, and we've gone through these books, just learning some basic number theory here, and learning some basic, some commutative ring theory, integrality, and some more number theory here. And I don't know exactly what I'll be doing with all this information, but my advisor's taking me through a few textbooks, and in the fall she'll finally give me the problem that she wants me to work on with all this background material. So I'm not sure. I'm supposed to say, which doesn't make sense based on this presentation, I'm supposed to say representation theory, because that will be the main thing of what I do. But none of this is representation theory. So I will work in the intersection between number theory and algebraic geometry and representation theory. And so I will learn representation theory this summer. And next USTARS, I'll be better able to answer that question.
I'm assuming it's well known the fact of the integering of the cyclotomic integers being z adjoining that propensity to unity. But is your proof unique, or is that from one of these books, or just?
It is absolutely from one of these books. There's multiple proofs. That proof is specifically in here, in the first resource here. I've seen a few other ones. I really like this one because it uses trace and norm, and they're very straightforward. The definitions of trace and norm is very attainable. I saw actually earlier this week, I saw a different proof in the second book, but it uses facts about Dedekind domains and the fact that the ring of integers in any finite extension of Q is Dedekind, and you talk about factorization of ideals into product of prime ideals, and it uses more advanced stuff, but this is, I think, very attainable, so I think I'll show this one.
Quick question. Is it readable to your SML, or would I get better if I just took your size?
No.
Can you get that proof, or did you have to dissect with the completely terse?
I was able to get through it, so I'm sure you will. It was not. It was. I think it was a good. He wasn't too terse, but there were some times where he would say something, and he just made a sentence, and I'd have to flip back. It's like, oh, we did actually prove that. So the answer to your question is, it's totally attainable. I think it was.
So PSML, the book is fairly, it's good, it's fairly terse. There are easier books for algebraic number theory than Samuel's book. It's not impossible to read, but it takes a while.
And there's some times where I think because it was translated from the French, it's some things get lost in translation.